Oh, thank you for introduction. So today I'm going to talk about the classical proof of quantum knowledge for multi-prover system. This joint work of my supervisor Anne Broadbent and Alex Gerlo, me, and Arthur Meta. So the key words is proof system and proof knowledge. Oh, so let me start from the basic stuff. So when you have an empty language that is consist of a yes instance and no instance. And a famous example is a three-sub problem. I will explain this example later. And a second famous example is the integer factorization. Given integer n and k, you are asked to find a non-trivial factor smaller than k for integer n. And then if you have the empty language, you can also consider the interactive proof system for such an empty language. In this example, basically the verifier is a weak computation, but you ask some prover to compute some certain computation. And then in the interactive proof system, you usually consider completeness. If it's a yes instance, then there's some information such that it's useful to convince the verifier larger than probability 2/3. And then also you consider the soundness, namely if it's the non-instance, then no information helpful to convince the verifier with probability almost 1/3. And then if you consider the interproof system, you're also happy if you're happy to have the zero knowledge property such a proof system. What is the zero knowledge? So basically, by interacting with the verifier, you might leak the information about your witness. Usually, the witness is very sensitive information. You don't want to leak such information to the verifier, especially if the verifier is malicious. So pretend to be a good verifier by interacting the prover that he might steal your information. So now we have the concern. If the server is malicious, then the verifier could steal your confidential information. In other words, the prover doesn't want to review her information, for example, in the password or credential information. So zero knowledge is such a security condition to prevent this situation. Instead of sending the raw information of your witness, first of all, basically, in general way, is that first of all you commit your commitment to your witness, and then send it to the verifier, and the verifier reply with some challenge 0 or 1, and the prover's answer to this challenge. And then looking at the transcript, the verifier will decide reject or accept. And then in this way, thanks to the commitment scheme, the prover is able to prove if the given instance is yes or no, without leaking the information about the witness. So this is the basically the intuition of the zero knowledge. However, the zero knowledge is mathematically defined as follows. So how do we define the zero knowledge in mathematically? First of all, you consider the machine called the simulator that can interact with the verifier as in actual protocol. And the simulator sends some query to the verifier to invoke some reply. And after that, the simulator even rewind the verified state so that next time simulator send the query to the verifier, then the verifier's reply doesn't depend on the prior question. So in this way, the simulator can interact with the server and sometimes rewind the verified state. Then you can generate the transcript. The one is the transcript generated in the actual protocol, written as trans sub real, and then the right hand side is a transcript generated by such a simulator. So mathematically, the zero knowledge is defined as such two transcript. It's almost the same. By showing this, we say that such a proof system is zero knowledge. In other words, that it doesn't leak her information. Or you can say the transcript by the interaction is almost the same as the transcript generated by the server itself, because the simulator is basically asking the verifier to generate some response. And then finally, or you can say that zero knowledge is that actual transcript that generated by the actual interaction can be generated by the simulator. So by showing this, we say that the given proof system is a zero knowledge. So this is the security criteria against the malicious verifier. But on the other hand, we need to also sometimes have to care about the security condition against the potential malicious prover. So if you have the zero knowledge proof system, and then, for example, the verifiers accept some certain prover, but the prover might, this might happen only just because the luck. Prover might not have the right witness to convince the verifier. So in that sense, we have a question. If the server is convinced, then the prover actually possesses the witness Y to prove that the certain instance is yes or no. Yes. So that's the another question against the prover. So now we have to think, how do we define the prover knowing some certain witness? So like in zero knowledge concept, we defined the knowing or position of certain information is defined by considering the following statement. So mathematically, this question can be converted in the following question. If the prover passed some protocol with some property, then the witness can be constructed from the interaction. So here we define the prover knowing some witness by showing that you can construct the information of witness from the interacting with the prover. So this is how we define the knowledge. This is how we define the prover knowing the witness. So let me explain the detail using an example. So let me start from the, let me use the example of the three-set problem as an NP content language. Three-set problem is an instance as follows. So you're given, for example, three equation given enclosed by rectangle. You can see the x, y, z, s, and t. And then three equations follows some computation rule shown in the top right corner. And then you are asked to find the assignment 0 or 1 to all of variables satisfying this computation rule. And then this problem is known to be NP language. And then imagine the case where the Alice knows the witness. So you can easily check that this satisfies the three equation. And then the Alice wants to prove that this instance is a yes instance by using this witness. So in order to do that, Alice, first of all, since she doesn't want to leak the information about such a witness, so she employs the zero knowledge proof. So usually the Alice does commitment to such a witness, and then send it to the server. And the server asks Alice to review some partial position of the variables, for example, S and X and X, S and T, and then Alice respond with openings of such positions. And the server will know that assignment correspond to the position of X, S, and T, and then the server is able to easily check if it's satisfied or not. And then you repeat this process again and again, and then server decide accept. So this is the typical example of the general proof for a three-step problem.
Sorry, Nagisa,
Yeah.
just a quick question about terminology. So when we use the verifier and prover terminology,
Sorry.
so here the server would be the verifier and Alice would be the prover because she has the witness. Is that?
Yeah, that's true. Sorry for confusion. Yeah, you're correct.
Okay.
Yeah.
And is that so throughout the presentation that Alice is going to be the prover? And the server is the verifier. Is that something I can? Okay.
Yeah. Sorry, I forgot to replace the terminology. Sorry. Thank you for your question.
Thanks. Yeah.
So, but now we want to let's imagine that you are verifier or server point of view. You're more curious when you accept the prover. More you're curious if the prover actually possesses the witness or not, because the proof system does only care about the completeness or soundness. So let's assume that prover or Alice is accepted by the verifier with some property small p, and then you're more curious. You want to see if Alice possesses the witness. So let's replace the server or verifier by extractor. That is a kind of a machine. And then this can interact with the Alice. So like in real protocol, the extractor, Alice send the commitment to the extractor. And the extractor asks Alice to open some positions. And after that, extractor rewind the Alice state like you do with the simulator. And then ask Alice again the other position of openings. And then Alice would reply with openings. And then at the end of the day, the extractor is able to construct the witness. Remark that since the Alice prover is only accepted with some property P, so sometimes Alice would respond with the wrong answer. But that's okay. The extractor can try again. And then since the probability is P, so you can expect that the extractor is able to extract the witness with 1 over P trials. So if the P is inverse poly, then extractor succeed with polynomial times. So in this way, we capture the knowledge of the prover demonstrated by the interaction. So this is the intuition about the proof of knowledge. The summary, if you have the processing for NLP language, you first of all care about the completeness and then soundness. And then you also furthermore consider the zero knowledge. Think through this property, the verifier obtains no information beyond the membership of the X. And then this is mathematically shown by constructing the simulator. And then moreover, the proof system, if the proof system has a proof of knowledge property, then the verifier ascertains the prover's position of the witness, some omega. And like in the simulator, this is mathematically shown by constructing the extractor. Especially the proof system has zero knowledge and a proof of knowledge, then you will have the sort of counter-intuition conclusion. The prover is able to prove that he knows the secret witness without revealing it. So as you can see, this property is very helpful when you consider applications such as anonymous credential, or even the theoretical applications like CCA security problem. So in this sense, the proof of knowledge is kind of a fourth property of proof system. So I want to mention more about the definition of the proof of knowledge, because I already gave a sort of intuitional level of explanation for the POK. So from the given the prover that can pass the test with some probability larger than kappa, in order to prove the proof of knowledge, you have to consider the machine called extractor. This extractor can interact with the prover in a molecular way. And at the end of the day, the extractor must compute efficiently some valid witness for a given instance. So this is how we show the proof of knowledge for a certain proof system. So again, extractor with Oracle access the prover generates witness efficiently. And then classical setting, Oracle access means that extractor can rewind the previous state. And then also, yeah. Please interrupt me.
Sorry, we just had a doubt, like what is preventing the verifier from using the extractor to extract the witness? Like, is it that the prover is used as a subroutine in the extractor, or like does it make sense?
Sorry, can you say that again, please?
Yeah, like what is stopping the verifier from using the extractor to extract the witness?
Basically, because you can see the extractor have a power of rewinding the prover, so you cannot do this. The verifier cannot do this. So this is the theoretical machine.
So is it that the extractor uses the prover as a subroutine during rewinding? Yeah. Okay. But because
yeah.
Okay.
So even if you consider the zero knowledge property by showing the simulator is also a theoretical machine, and they use the verifier as a subroutine, right?
Okay. Also, is there any computational bound on the extractor? Is it like?
So the extractor must be efficient machine, efficient bounded computer.
Okay, but since the extractor has the prover as a subroutine, would this mean the prover is also efficient? Like, sorry, like I'm not able to like.
So the machine can prove it as an oracle.
Oh, the machine uses prover as an oracle.
Yeah.
Okay. So, and by efficiency, now we just mean like it queries the oracle like polynomially.
Yes.
Okay.
That's correct.
Cool. Thank you.
Otherwise, the machine, if machine is unbounded, so machine can compute by itself. So that's why we put some computational boundness to the extractor. So the one thing is the rewinding, as you do with the simulator. And the other thing is that the witness that machine extractor compute must be valid. So in the sense that it outputs the witness y such that tuple the x or y is satisfied the NP relation. So NP relation is trivially defined by NP language. But how about if the prover is a quantum, like in a post-quantum setting? How about if the witness is the quantum state? So first of all, if the prover is quantum, then you cannot rewind the prover state by nature of quantum mechanics. And then also, if the state is quantum, then it's not trivial about how do we define the relation? How do we assess the quality of the output state of extractor? So let me generalize it to the quantum case. The quantum.
What was the second point you said? That so one was you cannot rewind, and the second point was what?
So for example, so I'm going to talk about the QML language. And unlike the NP language, it's not trivial to define the QML relation.
The relation itself. Okay, I see. Okay.
Yeah. So I'm gonna explain it soon. Very soon.
Thanks.
So quantum version of NP language. So let me start with the NP language. As we see that the instance is accepted by output 1 with okay, a bit confused. Is instance, then some information, there's some hint, so that the machine output 1. If it's now no hint is helpful to output 0. So example is like a 3-step problem, like we saw. And then quantum version of an NP language is a QML language. If it's a yes instance, then there's some quantum state such that that you can convince the verifiers, some verifier with larger than 2/3. If it's no instance, no quantum size to helpful to convince the verifier larger than 1/3. And then the one of famous example of the QML language is the local Hamiltonian problem. Especially we will look at the XZ local Hamiltonian problem. This is a linear combination of some local Hamiltonian term, but each Hamiltonian term, h sub I, is expressed by linear tensor product of Pauli x and z. And in such a local Hamiltonian QML problem, if it's the S instance, then such a ground state is negligible. And if it's no instance, then the ground energy is very large. So this is the QML language that we are going to use. So if it's a quantum state and the prover is quantum, then prover must compute the valid witness at the end of the day efficiently. So we have to adapt the definition of the extractor in a quantum setting. So we modify the rewinding to the quantum rewinding. Namely, the extractor is able to run provers unitary coherently. So this is exactly what you see when you have the zero knowledge property in a quantum setting. And also, we can define the QML relation. The extractor outputs a witness must output a witness W such that probability of fixed verifier accepting must be larger than fixed probability gamma. So you can in order to define the accumulation, you have to choose some fixed verifier V and the gamma. So that's the small change from the classical setting, but basically the similar definition.
So do things change drastically? Like, are there known problematic examples where choosing a different V and a different gamma results in a different set of problems that admit a proof of knowledge? Or is it robust in some way?
That's a good point. First of all, why we have to choose the probability gamma is that in the QMA language, the verifier's accepting probability is not one. It's probabilistic acceptance, and that's one thing. And then also, and the end of the day, usually you can amplify this property.
Exactly. Yeah, that's what I would have thought. Yeah, you can get like arbitrarily close to one, right? Completeness and soundness. But,
yeah.
or is that not trivial? I forget now because there were some. Because you don't have so many copies of the witness, right? So there are some rewinding results for amplification. I forget. Okay. Sorry, maybe you can tell us.
Yeah.
Sorry. So what is the bottom line? Is it robust or we don't know? Or
what do you mean by robust? Can you
in the sense that it doesn't matter what verifier and what gamma you choose? Like in the sense that for example, for defining BQP, it doesn't matter whether you have like as long as the gap is bounded, like you can make it 1 minus negligible. Is it similar here that the choice of gamma doesn't matter, or?
I believe it doesn't matter very much.
I see.
At least it's not negligible. Unless it's negligible.
Right.
Yeah.
I see. Okay, that makes sense.
Yeah.
And the other thing I wanted to quickly check was that so for rewinding, does it matter whether you also give access to the inverse of the unitary to the extractor, or?
Oh yeah. That's true. Thank you for pointing out. I forgot to include that. So the prover is also run the U star inverse conjugate, complex conjugate of the unitary. Yeah.
Right.
Thank you.
And are
That's
there
a
like
good point.
examples where it makes a difference? Like, do we know like provably that if you only give access to the unitary but not the inverse, something becomes impossible? Are there like
I'm not sure. I think it depends on the protocol, proof system that you consider. Like in this case, we don't really use the complex conjugate of unitary. We only need a unitary.
oh,
But sometimes, like in a different protocol, like a Broadband Gray-Law protocol, they probably have to use complex conjugate of unitary. I don't remember exactly. Yeah.
because I would have thought that if they're only using the unitary, then maybe the verifier itself can also just. But maybe okay, maybe that's not immediate. So you're somehow saying that just being able to run the unitary coherently is already something that gives the extractor more power than the verifier has.
Oh yeah, that's the more powerful. Yeah.
I see. Okay. Thank you. Yeah, sorry for the interruption. Please continue.
Oh, that's okay. Thank you. So this is the quantum version of a proof of knowledge. Yeah. So let me go to the proof system that we are interested in the paper. So this is the final section of the slides. So we want to consider the proof of knowledge in the following proof system. So this proof system is two-prover proof system for QMA problem. Specifically, this protocol is called Hamiltonian game, discussed by Grillo in 2017. This proof system is a as you can see, the multi-quantum prover with the classical verifier proof system for QMA. In his paper, this proof system he argued that this precision can be used to delegate some quantum computation to the quantum prover. And also, this proof system is informational, theoretical, secure. And then I will explain more detail, but overall, this proof system works as follows. First of all, the classical verifier, since he's classical, so he cannot compute. And then instance the local Hamiltonian. Since he's a classical, so you cannot expect him to compute the ground energy. So verifier asks the quantum prover to calculate the ground energy of certain local Hamiltonian. Then prover replied to him with the classical reply to him in the classical communication channel. And the verifier end of the day knows if the ground energy is low or not to decide reject or accept. And then our goal for POK in this proof system is that when the prover has this protocol with some high probability, then you want to make sure if the prover actually possesses the ground state of Hamiltonian. Point is that this proof system, even if the prover is honest, such an honest strategy is not known to be the optimal strategy, in a sense that honest strategy might not be the optimal acceptance probability. So in this case, we are more interested in whether the prover actually possesses the ground state of the Hamiltonian without cheating it.
I'm sorry. So what do you mean by optimal strategy?
Sorry, optimal means the best accepting probability. The superior, maximum acceptance probability. Yeah.
I see.
So it sounds like a self-testing, and actually our proof system is proof knowledge is based on the self-testing, and then I will give an explanation later. Yeah, so let me explain more detail about the proof system. Hamiltonian game. So again, Hamiltonian game is another game for a XZ local Hamiltonian problem. Each Hamiltonian term is a tensor product of poly X and Z. Here, the provers are supposed to be entangled, and then they are not allowed to communicate with each other during the protocol. The system works as follows. The first of all, verifier sends the prover a tensor product of poly matrices like this. And then the prover perform the measurement on the private register according to the query receiving the query. So like in first qubit, they measure with the respect to Z basis. And the second qubit, they don't do nothing. They don't do anything. And then the third qubit, they measure with respect to X basis, and so on and so forth. And the prover responds to the verifier with measurement outcomes, plus one or minus one. And then looking at the such answers, the verifier decides accept or reject. More detail, the Hamiltonian game is consists of two different tests. The first test is the main test, energy test, called energy test. This can be used to evaluate the ground energy of the local Hamiltonian. First of all, first prover in this proof system, I forgot to mention, but first prover is supposed to possess the ground state of the local Hamiltonian. So the verifier asks her to teleport the ground state to the bulb, and then at the same time, Alice responds with the teleportation key. The next, the verifier sends bulb. The randomly choose the Hamiltonian term, and then send them the Hamiltonian term. Since each Hamiltonian term is a tensor product of poly X and Z, So query must look like this, and then Bob put the pop measurement accordingly to the private register. In this case, the Bob's supposed to do the pop measurement on the teleported the ground state and response with the classical communication. So in this way, the verifier is able to calculate the ground energy of such a state. But generally speaking, you don't trust the prover, even if you send them some poly matrix. He might not perform accordingly. So you want to employ the self-testing. This test is called the poly burden test to self-test if they share equal pairs or not, if they perform the indicated poly measurement honestly or not. This poly testing, like in energy test, unlike in energy test, the verifier randomly choose the random poly and send them to Alice and Bob, and then check the answer. The point is that the Bob always receive the same type of query, so poly matrix, so he cannot tell the difference of these two different tests. So if they pass this poly blending test with high probability, thanks to the self-testing, Bob should behave honestly even in the energy test. So this is how this process works. And then it's been known that this process has a constant completeness soundness gap. And then you have to modify the process though, but basically the structure is the same. But if you modify it, then you can show that this process has a zero knowledge property. Discussing paper Bob and Meta and Zhao 24.
What is the modification? Is it a small modification that they make?
Yeah, I believe it's a small modification. So in the original protocol, you just send them the random poly, but in this modification, you also choose a random poly, but number of position of non-trivial poly is at most 6. So 6 out of n qubit are only non-trivial poly matrix. The other positions are trivial identity.
Oh, that's curious.
Poly.
And how does that tie into being zero knowledge? Is there an easy way to see it, like intuitive way of understanding it? Or probably
I
not.
don't think so. Why
Okay.
yeah.
Okay, it's just being greedy. Okay.
Yeah.
Thanks.
So again, our goal for this extraction, our goal is that we want to prove this process has a proof of knowledge, meaning that if the prover win this game with high probability, the extractor, using prover as our goal, can compute the ground state efficiently. By showing this, we say that if the prover accepted with some probability, then prover must have possessed the right witness, which is proof of knowledge. Here, I have to make a small remark. In the Oracle definition, it's also slightly different from the what I mentioned before. So first thing is the same. Extractor can run the proofs entirely coherently, and then but the extractor can also put the quantum state on message register, even though the actual protocol is the classical communication. But when you discuss the proof of knowledge for this proof system, you allow it to put quantum state on the public message register. The proof itself is rather simple. So first of all, the extractor, which can interact with the prover. First of all, the extractor lets Alice teleport her ground state above, as in the actual protocol. And next, the extractor perform the sub gadget with Bob's register to pull out his quantum state, his quantum state that is teleported from the Alice. And then finally, the extractor correct this state by teleportation key. So in this way, it enables extractor to compute the ground state efficiently. And then we prove the claim. And then key technique here is a sub gadget in the second line. But this is the this comes from actually the self-testing property of this proof system.
Is it the usual swap gadget that they use in self-testing? Like at least the.
What do
I
you mean
don't know
by
what-
useful? Oh, sorry.
I was saying the usual, like the very first. I don't know, like the example that they teach, right, for CHSH or whatever, that you have that specific circuit that does the swaps. Is that similar to?
Yeah. I
that's
think it's
specific? Okay.
it's exactly the same as actually we'll see in the next slide.
Okay. Sorry. Please carry.
Yep. So the key technique is super gadget. That's only non-trivial part of this proof. So let us recall what the self-testing is. So this Hamiltonian game has a self-testing, specifically poly-Braiding test self-testing. What is self-testing or rigidity? Mean that if prover win a knockout game with high probability, then their strategy honest up to isometry V. Personally, I feel reluctant to say this can be proved by Goa's atomic theorem. But anyways,
Why?
I appreciate. First of all, so if you look at the proof, basically what we say is that some function is almost same as some representation. Some function satisfying some property is close to the real representation. But a representation of group generated by poly X and Z. So there's only one non-trivial representation on such a group. I cannot say in short words.
I see. Okay.
But,
Sorry. Please carry on. I'll ask you later. Sorry.
Yeah. But there's only one non-trivial representation on such a group. So yeah, I appreciate the usability of this theorem, but I feel like it's a bit overkilling theorem applying to setting in our setting. Yeah.
So you feel
But
that it
anyways,
should be a simpler proof? Is that what you mean? Or?
Yeah, actually you can
I'm not
prove
able
it.
to. Sorry. I'm not able to follow. You're saying that Gauss Hatami is not enough to obtain rigidity, or you
no,
think
no.
it's too strong? Like it?
Yeah,
it's
too strong.
It's too strong.
Yeah,
Okay.
Got it. Yeah, I feel like it's too strong.
Okay, got it.
Oh yeah, but I appreciate the usability of the theorem. A visual explanation of self-testing is that, for example, if you consider the knockout game with two non-communicated prover, And by nature of quantum mechanics, you don't know if they are really share the entanglement, nor you don't know if they are perform the right Pauli measurement, honestly or not. But if the prover success some non-log game, such as CHSH or magic score game, then their behavior up to change of basis, the behavior is determined as that they must share the EPL pairs and they must perform the correct Pauli measurement. So this is the intuition about the self-testing property. And then, however, this isometry B is turned out to be swap gadget. This isometry just enumerates the swap gate, like shown in the bottom right corner. Let me explain more detail using the circuit base. The middle two wires are prover's register, and top wire and then last wire is auxiliary register. First thing that you can say that even though you don't know about the prover's private register, you cannot access to the prover's private register, obviously. But if you apply the isometry swap gadget, then you can pull out the prover's register to the auxiliary register, and it turns out that the auxiliary register are almost the EPL pairs. Mathematically, you can write it down as follows. Moreover, if you ask them to perform some unitary Pauli X or Z, but you don't know if they are actually perform the unitary Pauli X or Z, but the distribution of the middle two wires can be simulated by first apply the solve gadget, and then followed by the actual Pauli matrix. Then the previous distribution generated by previous action can be generated by how to say first applying the solve gadget, and then followed by application of a Pauli matrix on the auxiliary register. So this is the two main big important property of self-testing. And again, so these two different VRBB is a swap gadget. So let's go back to the proof. We want to construct the extractor that can compute the ground state efficiently. In order to do that, first of all, you ask the Alice, who is supposed to have the ground state, to teleport her state to the bulb, to the other prover bulb, and then receive the teleportation key. And such a state must be teleported to the bulb, which can be written as a row 0 to AB. And then by communicating with the bulb side, putting the quantum side on the communication channel, the extractor applies the swap gadget coming from the self-testing property. And the extractor is able to pull out the bulb state to its private register. And then finally correct this state to produce the ground state. So this is how the proof works.
So
summary.
is this system also zero knowledge? Probably not, right? Because
yeah,
you're
yeah,
using the original. It is zero knowledge. Okay.
Yeah. So
I thought you had to modify the protocol to make it zero knowledge. No.
Oh yeah. So based on the modified version, we prove it proof of knowledge.
Oh, so even in the modified version, you're saying you can run the
Yeah.
same.
So sorry,
Okay.
I didn't mention it.
I see. Okay.
Actually,
And
we need furthermore make a small modification, but basically almost similar. So I didn't explain it.
I see. Is it the case that well, yeah, I guess it's probably obviously the case that even in the modified protocol you get quantum soundness, like the
Oh yeah.
the optimal strategy. I guess everything checks out. Of course. Yeah. Okay.
In the modified case, in order to get constant complete soundness gap, the prover needs to have a polynomial many copies of the witness.
Oh.
Yeah. I think that's a bit technical. But proof of knowledge is holds even where provers only has one state, one copy of state.
I see. No, I was just trying to understand why, like a malicious verifier couldn't run what you're suggesting in the previous protocol. So on the previous slide, what you had,
Yeah.
I was wondering why a malicious verifier couldn't also run this and extract the state. What
So
is
the first thing that when you consider the extractor proof of knowledge property, we allow extractor to unrealistic assumption. Namely, extractor can put a quantum state on the communication channel, but in the actual protocol, this is only the classical communication. The verifier only communicate with the prover with the class, and also the extractor can access the provers unitary coherently. That's not realistic.
okay.
Yep. Sorry, I forgot. Yeah, I delete the list audience window. So somebody's.
Yeah, so there's a question. Yeah, Shreya says.
Oh yeah.
So two things. First, we didn't exactly understand what Atul just asked. And
yeah.
The other one was so you said we have like polynomially many copies of the witness, right?
Polynomial copies in order to prove constant complete soundness gap.
Right. So wouldn't that also answer the robustness question which was previously raised? Like, because we have polynomially many copies of the witness, we could amplify it arbitrarily close to.
Yeah, so that's good point. So we didn't tackle with that question. If I understand your question correctly, so suppose that the prover possesses the polynomial copy of the witness, and then run the extractor protocol, run the extractor to amplify the quality of the state. Is it correct? Maybe I'm not sure, but one of co-authors mentioned that sounds doable, but I don't know how.
Okay.
Yeah.
Yeah, and the question which Atul just asked, could you just repeat the question? Like I couldn't understand it properly.
Question. So if suppose the Alice, suppose the prover passed the protocol with high probability, then you want to make sure that the prover must have possessed the valid ground state. That's
Right.
clear?
No, about the malicious verifier.
Malicious verifier?
Like,
yeah, I know. So I was just asking if a malicious why a malicious verifier couldn't run what the extractor was running, because it looked to me that you're not applying any conjugate operations, like you're not applying U dagger, so you're just running the protocol forward once. And the answer, and maybe Nagisa can correct me, was that the verifier is classical, so malicious verifier will also be classical, while here we are sending quantum things and running the provers coherently
Yeah.
somehow.
Yeah, that's correct.
Right,
That
right,
is the difference. Yeah. So I have another silly question. So does it? So now you're saying that the prover had multiple witnesses, but you're extracting only one witness, right? So there seems to be a bit of a gap in.
Sorry. So
we-
when you want to prove to
constant
see if
gap
there's a
or something.
constant gap, then
Then
you
you
have to
need
assume that
multiple.
the prover has one
Yes.
polynomial copy. But if you only consider the proof of knowledge, you don't have to assume such a assumption.
I see. I see.
But if you start from the assumption, prover possessing polynomial copies, maybe you could find a way to amplify the quality of quantum state by running the extractor polynomial many times.
Nice.
But I don't know how to do this.
Okay, thank you.
Yep. So the summary, so modified version of Hamiltonian game. This is a non-local game for local Hamiltonian problem. Quantum provers are entangled, are supposed to be entangled. They are not allowed to communicate each other during the protocol. And then this is a completeness, of course, and it's soundless. And then it has a, as I said, it has a constant gap between them. And the third property is a general property. The prover do not leak any information beyond the membership of the Hamiltonian. And the fourth property is sort of the sub-property, self-testing. If prover pass the Hamiltonian game with high probability, 1 minus epsilon, then prover must have been entangled with the API pairs, and also perform the poly measurement honestly. And then based on this self-testing, we show that this persistent also has the classical proof of quantum knowledge. First classical meaning that this persistent means a classical communication, and then second quantum, or meaning that we consider the proof of knowledge for quantum state. So that's why we put we say classical proof of quantum knowledge, basically proof of knowledge.
Can I ask a dumb question?
Yeah.
So for property 3, when you say zero knowledge, we are assuming does it make sense to consider malicious quantum verifiers that are sending? Yeah, maybe it doesn't make sense. Does it apply to also classical communication? But
Yeah.
locally, the verifier could do something quantum. Does that make sense? Or maybe it can.
I don't think so. I don't think
Does it follow
so.
immediately from the proof, or do you think it needs a bit more work to show this? Like this BMs at 24, do you think it just immediately follows from the work that even if the prover is locally quantum, everything goes through?
Again, I'm not sure about the technicality, but first of all, the classical communication for quantum computation is preferable than quantum communication for quantum computation, right?
Right.
So so in this sense, this example is more sort of advanced or useful than quantum communication model.
For sure.
So in this
That's
sense,
the whole point of having two provers, right? Otherwise, you could
yeah.
do the blind delegation kind of things.
Yeah, so that's why this example is more useful. So in the sense that we don't want to consider we don't want to downgrade.
No, they're not downgrading, right? Like you're proving something stronger. You're saying that not only is it zero knowledge against a classical malicious verifier, it's also zero knowledge against potentially a quantum malicious verifier. So it's actually strengthening the proof system stays the same, but you're trying to make a stronger statement that the security holds. It's like the post-quantum version, if you like.
Okay. I'm not sure actually.
Okay. Okay.
Yeah.
Hello.
Yeah.
Like in this case, is the advantage just that the verifier has like some kind of speed up, like when it's locally quantum, or do you expect
Speed up?
like, yeah,
What
like
do you
in
mean
the
by
stronger
speed up?
notion, in the stronger notion that Atul just described, it's just
Well, I
classical.
was referring. Sorry, at least for me, I was just referring to the zero knowledge property. So
Yeah.
the zero knowledge property is true against classical verifiers, right? Efficient classical verifiers, and I was asking if
Yeah.
one could extend it also to efficient quantum verifiers that are nonetheless communicating classically.
Right.
That's what I was asking.
Okay, I see. I see your question. But I don't know. I cannot answer the question.
Right. No,
I
I
don't
thought
know.
maybe it was obvious or trivial. That's why I thought I'd quickly check. But yeah, of course.
Yeah. Sorry, I don't know.
Yeah, of course. Yeah,
Um,
sorry. I was just, like I said, I was just curious. So I asked. Yeah, please continue.
Oh yeah, thank you. So this persistent also has shows the proof of knowledge, meaning that if the proof passes the Hamiltonian game with hyperbole, then the extractor efficiently compute the quantum state such that the quality of such quantum states is good. The energy is very low. Or you can say that if a proof passes Hamiltonian game with hyperbole, then proof must have possessed the valid quantum state. Yep. So implication is
Sorry.
yeah.
One more quick question about the previous
Yeah.
slide. So does the
Yeah.
I remember reading Rio's paper in which he also does verification. So does this point 4 also essentially allow you to do verification? Or does that verification probably just follows from the local Hamiltonian.
Verification.
Like verifying a BQP
Yeah.
problem, for instance. So this you can use to also verify BQP, right? If you have a proof system for KM, because you can just use the circuit Hamiltonian construction. And yeah, okay, sorry.
Yeah.
I recalled it while I was asking the question. Sorry, please
Okay.
continue.
Yeah. So in the final slide, let me say some implication or open problems. The implication is that we might be able to say this persistent showing the safe testing even for the ground state of local Hamiltonian. So usually safe testing only refers to the strategy, but in this setting, we moreover say that the safe testing even for the certain quantum state as well. But remark that assumption of pure proof knowledge and the assumption for self-testing is different. On one hand, self-testing doesn't care about the efficiency of isometry, but on the other hand, proof knowledge must consider the efficiency of computation. And also in the proof of knowledge property, we allow machine to do LOCC operation, local operation and classical communication. So by sending the classical communication, the extractor invoke prover some certain unitary. So even though there's a slight different assumption for this property, but one interpretation could be that the self-testing not only strategy but also the quantum site. The open problem is that perfect deletion. Perfect deletion is that you want to verify the prover actually lost the quantum state. In the extractor, by running the extractor protocol, the extractor pull out the quantum state from the prover. So that this technique might be useful to consider the perfect deletion scheme, or this could be can be used in a state complexity problem. In a state complexity problem, like state BGP, state QMA, where you consider where the provers expect to synthesize some certain quantum state. So as verifying the prover actually synthesize the state, the proof of knowledge machine extractor can be used to verify if the prover actually synthesize the state. The third property is if we compile these two multi-prover setting to the one prover proof system by applying the famous compiler KLVY21, then still a proof of knowledge is preserved or not. Actually, this must be preserved. So, so this is a open problem that I pick up.
Sorry. What did you say about the last thing? Actually, what must be preserved?
Even if you compile it to the one prover setting,
Right.
then proof of knowledge is still preserved or not.
Or
But,
whether or not. Okay. I thought you were
yeah,
saying that something is preserved manifestly. That's okay. I misheard. Sorry. Okay.
Sorry, yeah. Not sure, but I do believe that it's preserved. It's not. I think it's not difficult question. So that's all. Thank you for listening.
You mean because we know that at least for some games that the quantum value is preserved? Is that why you're saying that it's kind of straightforward?
No.
Because it's not known, right, in general, that all games have. I mean, okay. I mean, now very recently people have shown that they have the same quantum value, but
yeah, actually, so the other researchers do the compiler using the Alex Grillo's protocol, and then when I look at the paper, then I had an intuition that it's easily show that the proof of knowledge is preserved.
Oh, that's true, right? Because they are using that specific. Okay. Because you only need a bipartite game, and I think for bipartite games of this nature, I think they have.
Yeah.
Right. Okay. Got it. Okay. And do you think that even the modified version with zero knowledge,
yeah,
like do you think zero knowledge is also just as immediate as proof of knowledge in the compiled setting?
I believe so. Actually, I'm working on that with
very nice. Okay.
some colleague. Yeah.
We'll hear about it soon.
But I do believe that it's preserved also, as a knowledge part is also preserved.
Right.
But there must be other way around. Even start from the Alex protocol and then compile it, and then make it zero knowledge in the one proof.
Oh, right.
Yeah.
Okay.
So yeah.
I see. Interesting. All right then. I don't know if anyone else has any more questions. We asked a bunch of questions. Yeah, please go ahead.
Hello. Yeah, like just to poke like Atul's question a little bit more. Okay, so this I should have asked in the beginning, but the notion of zero knowledge is computational, right?
In this proof system, it's informational theoretical secure.
Oh, so it's perfect zero knowledge.
Yeah, perfect zero knowledge. Yeah.
Okay.
But I think it depends. For example, in I don't know. I think it depends. There is no restriction saying that if you consider proof knowledge, the zero knowledge part must be perfect. There is no such a restriction.
Okay. Because if it was computational, then like in the case in which the verifier is locally quantum, it's like some BQP machine, and BQP is inside CZK, right? Like computational zero knowledge. So this proof should also hold for the case in which the verifier is like locally quantum.
Oh,
but
yes.
With classical communication.
Sorry. What's the question? I lost.
Yeah, this was just an attempt to answer like.
Yeah.
So Atul had asked that if the verifier was locally quantum, then is there
Yeah.
like does the zero knowledge property still hold?
Oh yeah, so thanks for pointing out.
So it should hold
Since
because
this
AQP is inside.
since this is the perfect zero knowledge, so
Yeah, since it's statistical, is there a difference between
yeah,
statistical and perfect? I thought what you mean is statistical, is it?
as a statistically secure. Yeah.
Right. So if it's statistically secure, then of course you're saying it doesn't matter what the local computation power is, regardless of
Yeah.
whether it's quantum or classical. You could just simulate it. So yeah.
So I
does
yeah I
address
can.
it.
So this answers your previous question. So
Right,
this is secure even.
was.
Yeah. I forgot this important part. Yeah. Thank you for having me here.